From our discussions so far, you may have gleaned that motion has a lot to do with precise definition. As I said previously, we intrinsically have a graph of complicated motion ideas. In many ways, the concepts involved in motion are as complicated as those involved with quantum phenomena. It is assumed that motion is easier though, because we as living creatures have to have knowledge of motion in order to survive. So far, we have talked about general motion. Objects move and do so over time. Distance is inversely related to time. Acceleration is an intrinsic vector quantity. All of these things I've spoken as motion generally. Here we will look about two specific definitions of motion: average motion and instantaneous motion. Instantaneous motion is the motion at one particular time. You choose a value of time, say 10 seconds, and describe the motion at that point in time. On a velocity time graph, you could choose a time from the x-axis and state its velocity at that time. You could do the same for a displacement time graph. With displacement, the same is true for the scalar equivalents. What becomes difficult is equating properties of a different degree from these graphs. How do you work out the instantaneous velocity from a displacement time graph? How do you show the acceleration from a speed or velocity time graph? There are two techniques you could use to work these out. One is more complicated than the other, but it is ultimately more useful and saves time later on. The first method needs us to have an equation for speed and velocity. Now that we've established the difference between speed and velocity, I'm going to use velocity examples from now on. We have already said that velocity is displacement divided by time, as time and displacement are inversely proportional. This means we have an equation for calculating velocity given displacement and time. From our displacement time graph, we have values of displacement at various different times. In order to work out the instantaneous velocity at one point in time, we need only read off the value of displacement and divide by the value for time. For example, the displacement may be 10 meters after 1 second. 10 meters divided by 1 second gives us 10 meters per second. The instantaneous velocity at 10 seconds is 10 meters per second. If we took a reading at 100 seconds and found the displacement to be 10 meters, we could say that this instantaneous velocity is 0.1 meters per second. These are the values that will be transferred onto a velocity time graph. So the profile of a displacement time graph defines the profile of the velocity time graph. The profile of the velocity time graph is the value of velocity as worked out from the velocity equation at each time. However, there is a different way. We know that velocity is displacement divided by time. What we need to be told now is how to work out the steepness of a graph. Steepness is another property that we intrinsically know. It is how far in one plane we travel for a distance travelled in a particular plane to it. More commonly written as how far up or down we travel for every distance forward. For a motion graph, time is always stepping forward, and either displacement or velocity is stepping up or down. The steepness of our graph, or more correctly stated, the gradient, is given by the height divided by the distance. For displacement time graphs, the gradient is displacement divided by time, and a velocity time graph is velocity divided by time. If we wanted to work out the average velocity from a displacement time graph, we would need to work out the gradient at a point. A gradient is calculated by taking the values of both the variables at 2 points, subtracting one from the other, and then dividing them by each other. In the case of displacement time, the gradient equals the change in displacement, written in shorthand as capital delta S, divided by a change in time as capital delta T. Technically, this gives a value for average velocity, as it is taking the average velocity between two time points on the graph. The displacement could vary wildly between these 2 points, but the average would still be as described above. Acceleration can be equated in a similar way from a velocity time graph. Acceleration equals change in velocity divided by the change in time between 2 points.